All right, successful start. So I believe this is where we left off last time, and I made the request that people try to write their appropriate filter to solve this lovely little problem. And we noted that essentially we need a ramp filter. Remember, we're going to write it MATLAB style, so it starts at 0 and the window is going to continue on from there back to just before 0 of the next pulse, right? So not a centered one, a skewed one. So was everybody able to do that? Yes. Did anybody notice the interesting issue? You do have to think about the number of points in the window. Yeah, so it matters whether it's even or odd, just because that the issue comes at the highest frequency. Is there a point that corresponds to the highest, or do you have two, right? So that's really what it comes down to. So theoretically, you should have something that looks kind of like this. I went in on this last Wednesday, that's why I was downloading and decided it was kind of hard to see where I was adding new stuff, so I went back and highlighted where the code gets added in. So I'm hoping this will make it a little bit easier to see. Really, honestly, it's the same basic thing, right? So, it's 2 divided by the number of projections because you're dealing with half of it. And obviously, this one is checking if it's even, this is odd. So if it's odd, I got to remove that one when you're walking in. Other than that, it's basically the same areas, right? So this one goes 0 to 1 when it's odd, right? Same up there. But when it's odd, we have to have that second point, right? Because you'll have one at the middle, but you'll have 2 on the other end. So I have to go 1 down to step, whereas this one's 1 minus step because there's not 2 at the end point. That's really the only difference between them when they're going through. And you could do it without having to define step over there, but you use it like so many times, it's so much easier to read as code if you break it out. Plus, it saves some calculation time. All right. Now, the other question that comes in has to do with, imagine this for a sec, is our object that's going through. And we've got here's our center line where it's coming in. We're going to assume our detectors down here are centered. We not only want this filter, but we want to know where the detector is located. Like not just where the center one is, but where each one of these. Right? So in this case, I think I put like 11 in here or something like that. Yeah, 10, 11. Right? And this one is, of course, the even one, and I put 10. So all that, nothing magic about that. I just drew a rectangle and put boxes of a decent size. And, they ended up looking nice and square when I had 11, and I cut one more off to get down to 10. But again, you'll notice that same thing happens. I also marked the minus P2 and P2, just so you understand, the same thing like step. It's really just an efficiency area to find them, but it does make it nicer when you're defining these. So what we want to do now is to say, can we locate each one of these points? This is going to become really important when we smear it back along a path. We have to know what those offsets are. So as long as we're defining the filter, the detector locations, is exactly the same size as the filter, because the projections are really just that you're going to take on based on those. So I want you to take it on this one, right? Given that I know the number of projections, how can I find the locations? Does that make sense? All right. So try to calculate what P2, the most extreme, and its symmetric point for even and odd. And let me just ask you for a second. How is it going to be different from, the odds to the evens?
Odds are going to be integers and evens are has.
Yeah, because that's going to be 0, so you have 1, -1, 2, -2, so on and so forth. Right? Whereas here, I'm kind of splitting between them. Right? So since these are all, we're going to assume 1 millimeter wide, it's pretty standard size shape for them. You know, since this is 0 and that's 1, the midpoint of it is at 1/2. So then, given the number of these, you got to have them go, you know, 1/2, 1.5, 2.5, both up and down. Okay, based on that and the number of projections, which you've got from the setup area, can you calculate P2 and the vector of detector locations?
So for the problem you gave me,
Yeah.
you have to like curve the detector location. What you have to do, like, I was thinking about it. It's like a square. It's like a portion of a circle, right? How would I?
So you could do it by an arc that's projecting back, right?
Yeah.
So you could do an arc. You can use slimes. That will then just follow those paths. You can then you can also make it completely non-parametric by
So yeah, you can go ahead.
selecting the locations of A.
Well,
Right? Because if you just arc them like in the square,
You guys started this on the last session.
that's essentially what we do.
I'd probably have to catch up then.
yeah, well, I mean, we didn't do a whole lot.
When you do the smear path,
Two
right,
lines,
it's
and then
being
those
done
things.
across those areas. If you did them one at a time on the smear back and then
Yeah.
between them, you could use the ASAP matrix. If you have a parameterized equation, then you can do what we do for the linear equation. Right, we'll calculate it like it's going to be x and y a little bit, and then we'll have a linear equation that describes the path that it follows. You would replace that linear equation with a line or whatever else it is. An arc segment is an arc segment.
And so like that equation would be based off of whatever the detector is like.
Whatever the path you're saying is traveling.
Okay.
There. And as long as it's something that's in terms of x and y, and you can write it as a statement, you'll have the x and y source that's full matrices, and it'll calculate the equation and make the resulting where was it one. And then it can use that to interpret it. That's probably the easiest.
Yeah.
No, we're making it.
But you can calculate that.
No,
You know,
this is
the
this
matrix,
function.
which is the line that's
Okay.
along.
So when we
Using
when we
whatever.
create our file, are we
But I think that's it's most
is it
similar.
just a script or is it like
Yeah,
But it will then,
we're
the
making
interpolation will then
function.
apply, because it just
So
goes between the grid.
if your file contains that.
It kind of makes it fun anyway. Yeah, just a little bit different. All right, everybody get their values? So and it should look something like this, right? I in particular am using floor for this because I know I'm on the positive side. How does anybody know how floor rounds?
It truncates to the closest to 0 value.
And in particular, we'll also say that it's actually when it goes towards the negative zone, right? Floor means it's going to go towards negative infinity, and ceiling goes towards positive infinity. We're on the positive side, so it makes no difference.
Okay. Yeah, I thought it was.
But I like this one in that, you know, it gives us a nice reference area, and we don't have any uncertainty with them. Right now, for the even one, which we're doing here, this is an unnecessary calculation. Right? Floor of projection divided by 2. Because you already know projection is divisible by 2. So projection over 2 is going to have a 0 value. Right? So I could just do projection divided by 2 minus 0.5. Right? Now, if I did that, think about this one down here. Right? Projection divided by 2 when it's odd, what's it going to be?
1/2 less than this.
So it'll be, yeah, it'll, you know, if I had like, you know, 5 projections, right, it would be 2.5. So it's going to be something 0.5. So I could do projection minus 0.5 here also, because this one's always going to round down, right? And projection divided by 2 minus 0.5 would be the correct answer for this one as well. It gives you kind of a cool situation. Up here, P2 equals projection divided by 2 minus 0.5. And down here, you could also say P2 equals projection divided by 2 minus 0.5. Right? Now, why then write it this way? The other one clearly is a simpler calculation, right? It works for both.
Easier to see.
Yes. Understandability, right? You kind of have to, even though that's not a complex equation, why it works out in both cases, you have to spend time thinking on. Whereas if somebody saw this, they just go, oh, you're just dropping off any extras. Oh yeah, that's the even one, so it's going to have it, right? This is readily understandable, even though it's a more complex math formula. And I would argue in the long run, this is what really matters. Because you are not going to run any particular piece of code forever. And even if you come back to it in like a year or so, are you going to remember every little shortcut you did? Yeah. You don't want to spend time having to think about it. So the cleaner you write your code, even if it's a little more complex, is going to be more maintainable. Now, if this is something that ends up running a bajillion times, right, you might want to put that in the comment and then put the shortcut equation underneath it, right, because then the extra calculations will become significant. All right. After that, the rest of it is actually the same, right? Detector location equals minus P2 to P2. We have to do the prime because just to get into MATLAB thing, it's just transpose. So realize I could technically be completely correct by pulling out, you know, remove the floor and just take this one out of this if, and it works for both. Right. But again, I do think this is a little easier to document and remember. So let's kind of think about what we've got going on here, right? So this is just kind of a little example I saw that was kind of small enough to do it. It uses a spatial filter mask, not a frequency domain. Yeah, you're welcome if you want. Like the code is completely up there. You're just building the code for yourself when you're going in. So if you missed the previous one, you can just start your own code. And when we're hovering on one of those pages, I show you the full code each time and just re-add the bits in.
Okay.
I think it's a lot more fun to kind of build it on your own.
Yeah.
Right? So anyway, the idea of this is they show you here's one particular ray path coming in. That's what's measured. Next one measured. Next one measured. Right? You're going to convolve it with this filter mask. The -1 to -1. And if you think you've got your ramp filter, which is basically a triangle, if you take that triangle and take the inverse Fourier transform and truncate it into 3 points, then rounded to the nearest integer, you know, that's the scaling you would have. Right? So this is a reasonable if you just did 3 pixels. We did quite a bit bigger than that because we've got a lot more sensors than that. And we're doing one that fully spans across it. It gets pretty small to the outer side elements. But, you know, that's not a huge loss to us. This still will work for it. It's just not as precise. The boundaries of this on the outer edges will be a little bit ugly when they truncate it this small, because you won't get the full width of the image cleaned up, but the actual image itself will be good, which is all they really care about for a simple thing. Right? Then they take those same things and they back project whatever you had and get your filter here. So that's the idea. We now have a filter. We have the locations and everything. So what we need to do for this, right, the back project along the lines, well, we know the detector location, so we know where we have to smear it back from. We know what the filter is, so we can replace a simplified version like that by an accurate filter for a ramp. And away we go. All right. So I want to include this. This is from the book because it shows a little bit of the difference in the same thing. This is that earlier example we had with the dots that were rotated. And this is, see the white line? That's a profile through where you can see the spikes for the dots kind of summing up. When you put this high pass filter through, notice each of these dots forms kind of like an outside spike, right? So you can imagine when I do a high pass filter, where's my pen? There it is. When I'm doing the high pass filter is going to catch the edges and it'll zero the middle out of a rect like this. So you'll get that kind of spike up on each of the edges, right? And that's what you're seeing happen here, is that you're catching those edges. And they spike up or down because in reality, nothing is smooth like this. So an edge here is really kind of, you can imagine, kind of rounded. So what you're going to get is, you know, if I'm coming into an upward spike, right, my slope is increasing. And then this is going back the other way around, right? So I get that kind of a shape to it as it goes past the inflection point. And I'm going to get similar for each one. If you look, that's what you're getting. You can see the up downs on all of them, and it's showing you. And nothing is smooth in the middle, so instead of dropping to zero, you get that kind of small noise on the in-betweens. But otherwise, it's the same idea. Notice the background is gray, though. Why is the background gray?
You can't plot negative numbers.
Can't plot negative numbers. So when they show it, it's not actually gray. It's actually still zero. But in order to show the negatives, they have to shift the whole image up. Right? And they scale it. All the negatives go between 0 and 1/2, and all the positives go between 1/2 and 1, and they just scale into that region. So that's why it looks gray. It's not actually gray. It's just to let you see the negatives. And those negatives will cancel it out. So when I take that single row, and this is the same row smeared backwards, you can see how there's the light and dark bands alternating, which is kind of giving you the edges of that object. That's basically what a sharpening filter does. So this is going to scrape and sharpen those images, removing the blur that's around it. So that's effectively what our system looks like. So this is what we're going to effectively build up. I thought this was actually a pretty nice picture, assuming starting with that location. This is their full cytogram. And so if they just did the reconstruction using the 40 of the bottom here, going up, that's what you get there. When you go up to 80 of them out of the 240, you get that image. And you can see it coming in, but it's still not perfect because you haven't gone the wings. When I go to 120 to halfway, they're looking pretty good, right? Because at that point at the 120, you've got them halfway around, right? So you can see the shapes nicely. And then the 240 here, and then they cut off the negatives. Right. On all the other ones, there were pluses and minuses, but by the time you get to this one, there still will be some minuses. So don't get mistaken on that one, but they just truncate them off, because it's gonna be so small, it'll just be noise. And it should have all canceled if everything was perfect, but no computer is perfect. We can't even perfectly hold the data, right? Yeah, I mean, we can like hold a half really nicely, but how about 0.1? We can't hold 0.1 perfectly in a computer. Kind of a funny thing, but there's machines don't actually have enough memory. If you were to try to hold that as a floating point number, you can't hold it, right? This is roughly the same as trying to, in regular numbers, say what's the decimal representation of a third, right? 0.3333, but it's not 0.333, right? Because you cut some stuff off. So if you want it exact, you have to keep going. Anybody know the rule to that? Like how to know when division by something is going to terminate and when it's not. So believe it or not, this was actually solved by the ancient Babylonians over 5,000 years ago. That's kind of a pretty cool thing. This is part of the reason why they used base 60, was a result of this understanding, right? If the base you're dividing by has the same prime factors that are in whatever you're doing your division on, it'll terminate. So since when we're trying to do in base 10, it's got 2 and 5. That's its prime factors. If you're dividing by 3, your division has the prime number 3. It's not in the base you're trying to use, so it will never terminate. Right? The reason why 1/10 doesn't terminate in binary because you need 2 and 5 to represent it, but you only have 2. So that's why it doesn't terminate. You can take a look at anything you want, right? You know, 1/7 isn't going to terminate for either one also, because it carries on. So you've got whatever you're dividing by, find out whatever the prime factors are. If all of those same prime factors are in the base, you're fine. If it's not, it'll just keep on going, and at some point you have to truncate. Yeah.
Why is 1 a factor of all bases?
Because it's not a prime number. By definition, prime numbers start at 2. Right, so when you're doing the division problem, you know, we don't count. But yeah, I mean, if you were to do that, you know, prime numbers, if you were to say, let's extend it and count 1, right? Then you could also say, hey, look, I can do it in base 1, right? Anybody know what base 1 looks like?
Just a bunch of zeros.
It's the hash marks. When you do hash marks and add them up, that's base 1. Right? The hash mark is there if you mark them in. You know. So, strange things, okay? But yeah, if you ever see kids doing mark 5, right, that type of stuff, they're just grouping together them. And you just count up all of the ones in your representation. And that's funny math notes. Anyway, the point of this one still comes down to, right, when you get to this final area, don't expect it's going to terminate because you're not going to get neat numbers, which means it's going to go well beyond whatever you can represent. So some things are going to get lost in the calculation, right? So the fact that it loses a little bit of noise, if you're careful with your calculations, it won't lose anything important. That's what will really matter. After we can see it come back. So that's our goal, is to do this, right? We have to apply the filter, and we'll apply it to these sinograms, but we only have to do it as we hit the row. So we're going to do it just in time style. We're going to apply the filter to a row, then we're going to smear it back, and we're going to add it to the sum. And we'll just keep adding them up until we get the answer, and then we'll do final cleanups to get rid of like the zeros and everything else. Make sense? Awesome. That's what you're going to write now. Okay. So I guess I should have added the 4 angle, right? Equals 1, you know, and then to the inner end, right? Inside here. That's just, we have to do it for all the angles, right? So, you know, just write your MATLAB code, right? We'll have the 4 angle equal 1 to angles, right? Angles is one of our variables. That's how our main are in there. And, you know, so we just do between the 4 and the n. And then I've already got the comments in there, right? The filter data. That's why I promised I would give everybody the code after today. I'd give you the PowerPoints to this. So, I didn't want to give it in advance because it cuts the fun out because you just skip to the end. Yeah. So you'll walk through all the angles. We have to do the 3 steps, right? Filter the data, find the projection line. So we know the start, so we have to find what the projection line is, right? And for those of you who have done it, that's where you would alter it to like a curve. If I was doing it along curve paths instead of straight paths, all I have to do is change that find projection line step. And then once we know the line and we know the data, then we just do the back projection with interpolation between those lines to get smoothness to it. And we're done. So we're really pretty much 3 steps away from finish, believe it or not. Okay, so the step is, how do I filter this? So I want to filter one line of the sinogram, right? In particular, the sinogram at that angle, right? We know where the sinogram is. It's called sinogram, right? And you know the angle is the second of my 2 dimensions off there, right? Rows, columns. So, yeah, because MATLAB is MATLAB. So it's not actually this picture, it's not. But don't worry about it. Just take MATLAB's ordering, and it'll essentially be the same. So how do I apply a filter? Right? We've made your filter. How do I apply it?
Well, one of them's got to move from the time frequency.
Where's this one?
Frequency.
It's in frequency already, right? And it's already a column because in MATLAB, the angles are along columns instead of rows like everybody else in the universe, right? So we already kind of wrote, that would be the one thing I would just have you note, is just make sure you do have that on your filter. Otherwise, your filter will be like this, anticipating a normal situation, but MATLAB's sinogram angles are going to come in like this, and you won't get a good multiply. Right? They have to be the same, and we're doing an array style. Right? So you have to take the sinogram into the frequency domain, at least that particular row. You can do a 1D FFT for that. Right? And then I have to multiply that by the filter, then I have to bring it back out. So apply your filters.
Is it easier to move the sinogram column into the frequency or to IFT or?
Good question. So let's ask the thing. If I were to do this operation in the frequency domain, how do I combine 2 different vectors? Element-wise multiplication. So if there's n elements in it, how many multiplies do I have to do? N. Okay. If I go back to the time domain, what do I have to do to combine them? It's convolution, right? So what is convolution's complexity?
N squared.
N squared if you do it the most obvious way. If you do it the faster way, which is actually FFT, it'll cost you an FFT, which is n log n, right?
Okay.
So, but anyway, you cannot do it faster than using the frequency domain.
Okay. Is there any advantage to just putting your filter in the time domain and so you don't have to do an IFFT every row?
Because then to apply it, the fastest way we have to apply it is to take the FFT of both, multiply them, and bring them back.
Well,
So to avoid the FFT, you end up having to do an extra FFT when the filter back in.
Okay.
Right? You could write a convolution that's directly in that area utilizing it. I've done it before. It is a task you can do. The problem is it will never be as good. And the reason is not because of math. It's because of practice. Right? People spend a ton of time optimizing the heck out of the You literally have millions of engineers using this all the time. And so people write all kinds of little efficiency tweaks and tunes, which you get to utilize when you do it here. You can write something that's n log n for convolution, but you're not going to have millions of people constantly tuning it and thousands of users who are just dedicated to keeping that code up to date and making it work well for a particular hardware and memory structure. So in the end, while theoretically you could achieve the same effect directly into convolution, it's just not maintainable.
Okay, cool.
So, and part of the reason why I give you the longer argument is these are reasonable questions that will come up. And so when you're looking at, hey, I have to write code as an engineer, and your boss is like, well, why don't you do this other thing, right? Knowing when it's more efficient to use generalized code and why is good to be able to explain, no, I'm doing it this other way, even though it looks like more steps, because it's actually going to save you and be maintainable code. I worked in industry for a while, and I can't even tell you how many times I had to make arguments like that to people. Yeah. Okay, we're good? So there is one trick you might notice on mine that might be different than yours, right? FFT sinogram, colon, comma, angle, that should be pretty standard for you, right? Dot times filter, right? Element-wise multiplication. I do the IFFT for that, yay. But then I have real. Why?
You just want the real part of it.
Yeah, but should it be real? Yeah, it should be real. But the calculation was done on a computer. So any of those little finite errors in computation can give you a tiny, even if it's like 10 to the minus 16th I, it'll still be a complex number. Right? So you'll sometimes get these ridiculously tiny, complex or imaginary parts making it a complex number. So it's, 99.9999 whatever real. But MATLAB is going to go, nope, darn it, it's complex. And when you try to use it later on, it will bust you. It won't let you show the image. It'll do all kinds of other crazy stuff. So by just doing real there, you throw away uselessly tiny bits and make your code avoid those errors. I was writing last week some code for some data we're working on trying to analyze and identify high energy nuclear particles coming out of an accelerator. And there's some uncertainty and some other things like that. And I wrote this code to calculate the uncertainty and map the uncertainty boundaries around it all there. It was working awesome. And then early this week, we hit some data where it had a problem. And that it was, again, one of these type of little things. I hadn't, because all of our data was supposed to be real numbers and everything, I didn't put checks to make sure it was in those regions because it would just slow down. We were doing like literally hundreds of millions of data points that we were working through. And one file had an error on just a couple elements and it just blew the code up. So I had to go back in and write the protection stuff because then I didn't know in the future whether we would hit them. So everybody had anticipated, and the error happened on line 90,000 or data element from the sensors coming in. This was real data. Was on line 90,092. I still remember the number because I had to hunt through to find what's going on with this data, and so I started checking for weird data bits. And it's just one of those things. You never know when it's going to come in. So protect yourself. And I say that, and then I skip it to be fast, and then it bites me in the butt. So, it's usually best to be overly protective. All right, now we have to do the calculate along the lines. And this is where it would be different if you were going along a curved path. Lines are so simple. I put this in, I just grabbed the slide that showed. This is the classic image that's shown on pretty much everybody's. And when you look at this, right, here's my line, here's my point, lines of the origin, there's theta, this is sine theta on this side, cosine theta times whatever that distance is, right? Looks really nice and standard. And they just say, hey, from looking at this, you can readily see that m is minus cosine over sine. Right? Now, when you look at this, does this suggest to you that that slope is minus cosine over sine? What would you think it is? Sine over cosine is going down, so minus. Right? Now, they're actually correct, but the picture is badly representing the information that they want. Okay? So what I'm going to do is try to explain, because you can see that I've reproduced all their salient information up here. You would not suspect that the slope of this is cosine over sine.
Is that because we're looking for normal?
Yeah, because we're looking at the normal on this one. And it's a little bit weird because most people go, oh, that must mean theta is up here. But it's not. Right? So this is taking that same one, right? If I rotate 90 degrees this triangle, theta rotates to there. Right? So, and that is a 90-degree approach. So they've neglected that bit. So theta is kind of in a backward spot than you're used to seeing it. Normally when we draw a triangle like this and we're talking about, we put the angle we care about here. Right? But that's not where it ends up because we measured from the origin. You have to preserve the triangle shape. Right? So it's just one of those things that's a little bit misleading the way it's read. You can then see, since the angle's here, cosine is the vertical and sine is the horizontal because my triangle is rotated 90 degrees. And you can do the same thing with, cosine or sine, of 90 minus theta. Same idea, right? That cosine 90 will come out and flip the particular one. But I wanted to calculate everything. So it's obvious, I think, here that what m is. Now that you see this extra triangle, right? You have no trouble seeing, oh yeah, it's rise over run, right? And the rise is minus cosine theta, and the run is sine theta. Boom, that makes sense. To get b is the intercept, right? So that's b. But I want you to notice that this angle theta here, since it's 90, means this is also a similar triangle with theta on this side, right? Because of that, I've got a relationship between b and s, right? So you can readily determine what it should be, right? And in particular, right, we can solve for it, right? If this side is b, right, then this side has to be b times sine theta. So b times sine theta has to be equal to s, which means b has to be s over sine theta. So we often just label that one as s over sine theta, and you can see it there. I don't think that's obvious as to why it is. So you'll see it in every graph because it's the net result. Right? Once you've seen it once, you'll understand why. Right? And then it'll make sense from then on. But that's how we get those two different components when we're calculating them. So what I want to do inside here, and I introduced, so you'll notice I put some extra data over on the other side. This is actually the point when I realized I needed to highlight it because I realized I was adding some stuff back there on the other side to kind of make it easier because that's the logical spot in the setup data area. All right. I added the n over 2, which is just because I didn't want to keep calculating floor n over 2. It's the same thing. It's a little shorthand. Right? And I wanted to make a mesh grid. What's a mesh grid in MATLAB?
It's a 2D grid with only your x dimensions. Or it's, sorry, two two-dimensional things.
Yeah.
One is your x, one is your y.
Yeah, and it is like the worst memory waster in the entire universe. but dang if it isn't also the most convenient notation that's out there, right? Particularly if you end up rotating and doing all kinds of other weird calculations to it. Just having a corresponding grid that has it, you can imagine if you just tilted this a little bit, your X's and Y's would all shift, and now they're no longer perfect. But you could still have one that shows me what's my X values and my Y values in the grid, and they wouldn't just all be copies, right? When we make rectilinear, it makes a lot of sense to reduce it, but then it wouldn't be as nice for other areas. So just note, right, this is a way to make giant two-dimensional grids of the right size, right, the image size, that just says what are the, from one the X, the other the Y coordinate of everything. And then it can just do a lookup when you do calculations. So what I want to do is calculate the line location. You have an equation for the line, right? We've got M and we've got B. So we should be able to, using those X, Y's, we should be able to calculate your location. Does that make sense? Now, we can simplify over this. I didn't include a simplifying of the calculation, but if you imagine for a sec, right? Y equals M, this, times X plus B. All right? Now notice on the side where the calculation is being done, S over sine theta, and I've got minus cosine times X over sine theta. Notice both things are divided by sine theta. So what would be a good thing to do? Multiply through by sine theta, right? So if I have y sine theta is equal to minus cosine, or x cosine theta, right, plus s. That's a much cleaner expression. And then I can take everything to one side. So if I'm on the line, I would have y sine theta plus x cosine theta minus s equals 0. That's the definition of the line. You always get your equation so it's equal to 0. The book has a little picture that I don't think obviously makes sense after that, but if you do that alteration, right, y sine theta. So we often do s as an abbreviation for sine, right, so s theta is sine theta, right, plus x cosine theta, right, minus your s, right, that value, the offset that's on here, we have this equal to 0, which means along that line, going through the origin, because we've shifted it, you in essence got to have that 0 line now, because we put the shift in. And if it's over on this side, it'll be bigger than 0. And if it's on this side, it'll be less than 0. Right? So this calculation right here tells you, am I on that line? Or if it's positive, then it's 0. If this is bigger than 0, it's above the line. And if it's less than 0, it's below the line. So it actually gives you that little identifier to find out where are you. Okay? So this is the definition of the line. So if I were to use those x's and y's, and for every grid center, calculate this equation and put that value in. If it was 0, it's right on that particular line. Right? If it was positive, I could tell how far off, because remember, we scale this so that it's exactly the distance away from the line, orthogonal to it. If it's negative, it's just going the other way. So now I have an exact calculation of where the line is. Does that make sense?
Are we just going to threshold that somewhere, or?
Yes, so we're going to put that in line location.
Okay, great.
So that's going to define for us the line location. That together with the detectors, which gives us the offset shifts for those, will be used in the back projection stage. Because this will define the line's pattern and which way up or down it is. Line location will tell us how much to shift it by. And that's going to be used by MATLAB has an interpolation function. So by calculating it this way, we're setting up our data to be usable by one of MATLAB's built-in interpolation ones, in particular interp one, but we'll get to that in a second. So I need you to calculate this line location matrix for R1. And realize, I could do this for a nonlinear. I still, all I have to do is get the line that defines whatever that shape of the curve is, where is it 0, with the offsets just need to be scaled correctly so that it can figure out what's the distance from the curve and it needs to know what side. But you could calculate any nonlinear function of x and y in there, and you can solve it. Make sense?
I have a question. Is theta, the input, going to be a vector of the actual angle samples?
So the theta coming in is all the different angles you have.
Okay, great.
Yeah. So in our case, when somebody gives you the sinogram, we could guess what that is, but you don't know, did they do 0 to 180 or did they do 0 to 360? Did they do minus 90 to 90, right? So to avoid that kind of, where does the position correlate to the number?
Right.
All we do with it is we pass a second vector that has the angles. So yeah, assume theta written out like that is just it's all the ones for it. So if I'm at angle, right, theta of angle is your particular angle reference number. This one should be fairly quick, hopefully. And again, don't worry as much whether you're right or wrong. Try to get as close as possible. Guesses are okay as long as they're educated, because we'll cover what the real answer is in a sec. But imagine yourself reading an article for the first time that's not really giving you a lot of descriptions, and they give you a picture that's not necessarily readable. You have to convert it and figure things out. So if you struggle with it, and then you see the answer, it'll help you to figure out how to do other ones in the future too. Okay. Yeah.
Do you want line left to be three-dimensional, or do you want to iterate through all the projection numbers, the projection sensors?
So it should end up being the same thing as a mesh grid would be.
Okay.
It's going to be for this angle.
Right. Yeah. Okay. So we're just picking one.
One angle. Because we're breaking up, it's inside the for loop.
Right.
So you're only dealing with one angle.
So I get that it's one angle, but since we have a bunch of different sensors.
Yeah, so the way MATLAB's that is a good question, and that's a function of MATLAB's interpolation.
Okay, so we're not going to worry about that?
We don't need to worry, because it just needs the 2D one to find the line, and then it'll just shift it automatically.
Okay, so we can just leave S as the vector?
Yeah, it's a two-dimensional.
Okay, great.
Okay, we're good? Okay, so that's what I had, right? For them. Yeah. Oh, I think I left off my phi when I couldn't paste the line. So phi is just, the theta of angle.
Right.
Right. So I should have had one line above that. Bad me when cutting and pasting.
Is there a reason that S term isn't there, the detector location?
Yes.
Okay.
So that is the shift. That S term is what's actually in your detector location offsets.
Right.
So this is the term minus the offsets.
I see.
Detector location has the offsets. So this is the generic one. Phi is just, remember theta is a vector. So theta of angle is phi. Or I should say phi is equal to theta of that angle. I should have had an whole line just before, but when I cut and paste, I evidently skipped it. So I'll add it in tonight and then post the full code to it. But that's the only change, right? It's just it's our angle here. And there was just a whole bunch of them, so you have to select them one at a time. So remember, theta is the same number, it's a vector with the same number of elements as there are columns inside a graph. Okay, we good? Yay. Okay, so this is just a reminder back here. Now we have to do this interpolation, right? Now, in order to do it, I could have just given you a term on you don't know what an interp is. But I started thinking, and that's what I've done in the past. But I actually think it's a good thing to go back and have you read. You go, hey, look, I need to find something to smoothly do this. I want you to take a look at the interp1 function. So I'm giving you the function. So you should be able to type help interp for interpolate 1. There's several different ones. Interp1 is perfectly fine for what we need. And it's the simplest. Just look at those files, knowing what you know, right? We know the detector location. That tells us our offsets. We know line location. We know filtered sinogram. That's what I want to spread back. So I want to spread filtered sinogram back along the line done by line location with offsets defined by detector location. So, take a look at interp1 and see if you can figure out where you think the parameters should be passed from their description in the help file. Looks like we might have enough time. I'm just going to launch MATLAB, which I can't easily do unless I stop the slideshow for a sec. Everybody doing okay? Have you found what you need? Yes.
It's all one-dimensional, so I'm confused on how we're gonna break it up into one-dimensional slices.
All right. So it turns out it's not as hard as you might think because it's broken up. The way we defined it is kind of broken up already. All right. So the detector location gives you where those offsets are. So that's kind of your one-dimensional reference line to them. Right? Filtered sinogram is what's going back, and line location defines the parameter. Right? That's what we did up here of, the pattern of how it's being spread back. And everything else is then just shifted versions along this basic offset. All right? So essentially you've got your offsets here, what's being spread back, and then what's the shape that's being spread back along. All right. Which makes it a fairly nice, simple way of doing it. And then we're just obviously, we needed to start with an initial zeros. I've unhighlighted it, but it was on the earlier one highlighted. Right, we just made an empty one with nothing in it. And then we just accumulate, right? I equals I plus. So we just smear and add, smear and add. Does it make a difference if I smeared the unfiltered one and then smeared the unfiltered all the way back and then filtered at the end?
Yeah, it's a 2D filter.
That's a 2D filter, but no. Otherwise, mathematically, it's exactly the same. You will get the same good quality image, but you are completely correct. The only difference is it's going to cost you a 2D filter instead of a 1D filter, and that's a bunch of 1D filters will beat a 2D filter any day of the week. So, yeah. All right. So now we just have to clean up, right? So clean up for your basic image, right? It's just going to be, I have to take that image and make it an image. Right now it's a calculated number. And you're not sure the scaling and everything else. So that function, matrix to gray, takes a calculated matrix and makes it a grayscale image. It handles all your scaling, maps it between the 0 to 1, corrects the data structure types and everything else. So it does all the nice conversions. So I just overwrite I because I really don't care. But that's a cleanup just so I have the right one so I can display it correctly in MATLAB. I also want to put on some amount, because I mentioned verify your data, right? I put the most basic verification that we could up here. Just make sure when they pass me, theta and the sinogram, do they have the correct number of angles in them, right? So we know that angles is the measurement for the sinogram. So we want to see, is that equal to whatever the maximum size of that theta vector? If they're the same, we're going to assume that you correctly sent me the angles for it. I have no way to check the numbers on them, so I just have to trust you on it. So if that's true, everything that we've just done is now in between that and the else. And in the else case, I just send you back an empty matrix to say, you sent me bad data, here's a nothing. All right, so if you get a nothing back, you sent me bad data. We could check for other things as well when we're in here, but this one at least gives you a simple idea of what it is. So at that point, we're done. There's our code, minus the fact I forgot to kind of base 5, which I'll have to add in, but that's not a bad one. Okay, so what does it look like? You get the one on the left, and it's a pretty good image. This is, a standard Shep Logan filter. You can see it does a really quite nice job. So it's hard to see inside the dark regions when looking on the monitor if there's any problem in the background. It looks really flat. So there's this thing called a gamma correction, which kind of stretches the colors or the gray space so that you can actually see a wider range of stuff in either the darks or the lights. And I stretched it such that we would get a good amount of stretching in the dark area, so the dark area became a wider range. So you can actually see, notice the kind of linear patterns coming through? Those are the angle smears. So you can actually see those angle variations coming in. Those are sometimes called streak artifacts or things of that sort. They're really small. I obviously had to, do a correction function to force it to become visible. If you look really well in the gray, you can see them in this kind of mid-gray one. You can see them coming all around from the outside area, streaking down from particularly near the bone areas and things. So you can see those streak artifacts exist in other spots. They are also in the background, as you can notice on here. But they are small and therefore not really a huge problem. But you should always know it's not a perfect thing. So I just included this one as kind of a fun numerical example. And it illustrates what I had said before about the -1, 2, -1. There's a good approximation, but you'll see what I mean by it. It only deals with the core because they truncated the filter that's doing it. In here, they just took, and the upper part there is just calculating from 4 directions what is the projections. So the upper left corner is basically, calculating these, the sinogram. And then you can see they convolve. 2 of them are identical because it's a rotationally symmetric image. So they just calculated the convolution for 2 of them because it does for the other 2 because they're identical. So you can see the appropriate size to each one. And then they just take those 2 for all 4 and they take them and they pass them back. So you can see the smears here, right? So, this is obviously horizontal and your upper left to lower right, the vertical smear, and then upper right to lower left. And they add those 4 together and you get that. Now, you might look and say that's not the same thing, but if you look at the scale between them, between the 52 and the -6, if you just consider them, right, you're dealing with in the ballpark range of what we've got for each one of those. You only took 4 directions, so it's not going to be a perfect situation, and you have too small of a filter on it, right? The reason why you get the scaling problem is -1, 2, -1. Remember we said there's a scale factor to your filters, right? This would be the same as -0.5, 1, -0.5. They wrote this one because it's easy for people to remember, but it's going to scale it, and they did it 4 times, so it's not surprising that it scaled this up pretty big, as opposed to normalizing it so the net result of all of those, absolute value sums to 1. That's, if you were to reverse that, you would scale it back down. It's off by about a factor of, whatever, 7 or 8 or whatever. But that pulls the number back down into a reasonable range. Notice the outer boundary goes like crazy. So it goes up again. So they were only somewhat okay in the 3x3 region. And that's because they did a little 3 filter. If they had gone to 5, it would have pushed that errors out. It would have drastically reduced the errors around 52, and it would have knocked the ones on the outside to about the same value as what's around the 52 now. So I think it's kind of nice to see if you truncate the filter too small, you'll associate it way too small with effectively good image. That's why we do the full width. It pushes all the errors way out to the outside and preserves things. That's why you'll sometimes in the corners notice there's a little more streak noise there. That's because that's kind of where the edges of our filter are. So the worst errors are going to be out there. Okay, make sense? Cool. So anyway, this is really just more of an understanding of what you just did. So we are technically through this whole lovely thing. So we should be able to, in MATLAB, run these. So we want to be able to do a test of these. So we're going to make a little new script. You've got an FBP code. We need data for this. So I'm going to have, an I true. All right. And this one, we're going to use the term phantom. So phantom's a command that makes these kind of lovely little Shep Logan ones. We're going to do 200. It'll give you a 200 by 200. By default, it'll do the modified Shep Logan, which is a perfectly good one. So I'm happy with that. We need a sinogram though. So we want the sinogram is going to be equal to, actually before I do that, let me do theta. All right. Theta will be equal to 1 up to 180. So this will give me, 1 degree increments, a full 180. And sinogram's going to want that. So I want sinogram, sino equals radon. And now I need to give it my image, which is I true. And we're going to give it theta. So this will now give me my sinogram. And then you can get your I, this is your estimate, will be equal to, in your case, FBP. And you pass sino to it and theta. And then you can image show I. If you want to show both of them, you can and figure subplot. And then we have to say, let's see, probably on mine it's wider than it's tall. So I want 1 row, 2 columns. I'm going to do the very first one. And I'll do image show I true. We'll put the true one up first. And then subplot I1 to image 2. Now, since I didn't put my version of this in, I'm going to use MATLAB as a built-in inverse FBP. So just for demo purposes, I'm going to put that one in. I radon and TTT sino. There we go. Oops, it's supposed to be IST. Okay, this will be test FBP. Okay. Now, if you run it and you have no errors, what did it get mad at me for? Well, it should. The old iRadon used to actually assume theta was the 1 to 180 was the assumption as a default, or at least on the old version of iRadon. I haven't used their code in such a long time. There we go. So they did make it explicit now. They used to just assume that it was 1 degree increments. But you can see they look identical. They're not really identical. One good way to actually see the difference, besides just kind of zooming in, you'll see some of the distortions there, whereas you won't see distortions over here. So you can see there is a little bit of a difference in them, even though they look really darn similar. That's some of that kind of structured errors we were talking about. One other way you can actually do it, and image show. So I can just take the difference between the two of them. Oh, I didn't. I should have bothered to put in the matte to gray, which I didn't. Here, as long as I'm bothering to put in matte to gray. I'm not going to put the absolute value on it, and then it'll do that whole grayscale shifting. Come on.
Yeah, it looked like they're different sizes.
Oh, did it? Oh, it's doing 202. So I want the middle chunk. Actually, let me just, I'm going to be really cheesy. It won't be exact. It'll actually that's a little too, it technically will scale it a little. So I'm probably better off actually. I asked 2 up to 201, 2 up to 201. I'll just take the middle chunk out of that one. All right. So you can see that it gives you, kind of where that uncertainty zone is. There's a little bit of a blur on the edge. So you can see where the edges are off. The bone is not quite as dense as it should be. That's on there. Again, remember, gray is the mid zone. When it's darker, it means negative. All right, so that's telling you that in reality, the true image is lower, right? Which means the reconstructed image has kind of the blurred edges. So when you see those dark bits, it's telling you that I'm too blurry on both sides of the edges here. And you can see that same slightly darker for all of the shapes. So that's the blur spreading out into it. That's just a function of the reconstruction. You're not going to get perfect because we have to interpolate stuff, and it's going to smooth it. It's just unavoidable. And like I said, when you get a consistent color region like going in here, that tells you, since they're so close together, it doesn't achieve the full height before it has to come back down again. So it never makes it all the way up. If it was wider, it would get closer and closer because, really narrow chunks of density, it's hard to get those accurately. I just think kind of rounding things off. If you came through with a file or something, you break a whole chunk off on a thin piece, you just round the corners and other stuff. But basically, it's not too bad. You can see they're aligned right and everything else. And so hopefully all of your images get similar results to that. If not, let me know and we can help you through them. Good? Awesome. I'll add my phi back in, and then it'll take a couple slide manipulations. So tonight I'll then put it up as a public release so you can see it. Next week, we're going to start taking a look at the alternate way of doing this by doing iterative reconstructions. So this one we'll go into. We'll particularly be looking at some of the ways to do them in parallel, because I think that's kind of more fun with them. If you're going to do it, you should do parallel. Other than that, I think we are good. So have a lovely day. 1 second.